Hello everyone and welcome to OneClass. My name is Jeff Kraus. I have a PhD in chemistry and today I'm going to run through a few undergraduate high school level chemistry questions. So here's our first one. How do you calculate the ionization energy of an element? So for ionization energy, okay, I had some technical difficulties here. What is happening with this? Uh-oh. Okay, sorry, 1 minute. Sorry about that. Okay, so we're ready to go here now. So back to the question, how do you calculate the ionization energy of an element? So in a simplistic picture, using say the Bohr model of an atom, right? We have the nucleus and we have electrons orbiting the nucleus, which this isn't perfectly circular, but and there could be other electrons, but our ionization energy is taking that electron from its orbital radius out to infinity. So removing the electron completely from the atom. Okay, so if we look, at least again from a simplistic picture, our energy should be electrostatic, right? So if we consider our electrostatic energy over R, then as R goes to infinity, this guy should go to 0, right? So E of infinity is R at infinity, which is just 0. Again, from this simplistic energy, which is not quite the energy of the atom, but one of the nice things is we can choose our energy to be 0 where we like. And so our 0 will be at infinity. And it's roughly, I would say, guided by this equation. Or you can remember that it's going to be 0 at infinity from this electrostatic equation. So our ionization energy is just the changed energy, so the energy at infinity minus the energy for the state in question, so whatever the orbital energy would be. But if that's 0, then it's just minus the energy of our orbital. And so that's kind of the nice thing, is that our ionization energy is just negative the energy of the orbital. As a simple example, for the H atom, the energies for our orbitals are given by minus r over n squared, where n is our principal quantum number. And so the ionization energy for a 1s state, where the 1 would be our principal quantum number, so that's just minus r over 1 squared, where r here is the Rydberg constant, which is about 13.6 eV. So that's minus 13.6 eV. Or our ionization energy is minus that energy, which would be positive, so it would be 13.6 eV. Sorry. Okay, so yeah, I think that's a pretty good description for ionization energy. So it's, if we check the written solution, so you can have an ionization energy from any orbital, but it would typically be the ground electronic state. Can be computed using Rydberg's equation, especially for a hydrogen atom. And so this would be yeah, so these are the energies, not the, so that looks good. Okay. Okay, so here's kind of a unit unit rearrangement question. Okay, so the Earth receives 1.8 times 10 to the 14 kilojoules per second of energy. What mass of solar material is converted to energy over a 24-hour period to provide this daily amount of solar energy? So our total energy then would be, if we're given this value for an energy per second, then we would have to multiply by, it wants to know how much total energy over a 24-hour period, so we need to get rid of the seconds, so it'd be 24 hours, because the time's on the top, or on the bottom in this unit. But of course our hours, we want to cancel with the seconds, so we need to multiply by 60 minutes per hour, canceling the hours, and 60 seconds per minute, canceling the minutes and the seconds. I'm just going to shift this down in case it's not visible. Okay. So then if we run this through on our calculator, we would get a value of about 15.552 times 10 to the 18 kilojoules. And then we'd round it to only two significant figures at the end, but for now I'm just holding on to everything. And now mass, we would calculate from E equals mc squared. So our mass would be, which corresponds to this energy, would be 15.552 times 10 to the 18 kilojoules, divided by 3 times 10 to the 8 meters per second squared. So that's just rearranging the equation. So now to get a unit of mass out, we're going to need this to be in joules. and then recall that a joule is a kilogram meter squared per second squared. So that'll cancel with the meter squared per second squared on the bottom and give you kilograms at the other side. So this would be 1,000 joules per kilojoule. So canceling the kilojoules. And so then, again, running this through on our calculator, we'd get a 173.04 times 10 to the 3 kilograms. Which if we round at the end here, because this is the mass that we're looking for, so it would just be two significant figures, so 1.7 times 10 to the 5 kilograms. Okay, so then the second part of the question says, what mass of coal would have to be burned to provide the same amount? Coal releases 32 kilojoules per gram. So for coal, we have 32 kilojoules per gram. So then again, we can use some unit analysis here to find that if our energy is 15.552 times 10 to the 18 kilojoules, then we'll end up with a mass if we divide by 32 kilojoules per gram, because then our kilojoules will cancel and the gram will come up top. And then if we run this through on our calculator, we would get 4.86 times 10 to the 17 grams. And it doesn't ask for a specific unit, so that should be fine. And again, two significant figures would be 4.9 times 10 to the 17 grams. Okay, so checking through the solution here, so we can, as I pointed out, we can use the dimensional analysis. So 1.6 would be the appropriate significant figures, but again, I prefer not to round until the end, partially just because you end up with some rounding errors at the end, like here. And to get the mass of coal, again, we would get around 5, so this is in kilograms, that's why it's 10 to the 14. In grams would be 10 to the 17. And so that looks okay. It's the difference in the 0.1 is likely, again, just rounding errors. So that looks good. Okay. Alright, so what is the boiling point of a sugar solution at atmospheric pressure? How do we calculate boiling point elevation? So boiling point elevation can be calculated with the Van Hoff equation. So here we have the Van Hoff factor, or not with Van Hoff equation, but with our boiling point elevation equation. So this is proportional to the number of species in solution. Okay, so for sugar, I equals 1. As a couple other examples, so for NaCl, which goes to Na plus Cl minus, I equals approximately 2. For calcium chloride, which goes to calcium 2 plus 2 Cl minus, I is approximately 3. So it's roughly the amount of species that are in solution But for sugar, it doesn't dissolve into anything, so it just stays as sugar, so I is 1. This is Kb, is our mole boiling point constant, which is computed for our solvent. So it's just R, which is the gas constant, times the normal boiling point of the solvent, times the molar mass of the solvent, over the delta H vaporization for the solvent. Okay, so these are all solvent terms. So for water, the gas constant for any species is 8.314 joules per mole Kelvin. Our boiling point for water, I'm going to use as 373.15 Kelvin, or 100 degrees Celsius. Our molar mass for water is 18.02 grams per mole. And, and that should be squared, sorry. And our delta H vaporization for water is 40.66 kilojoules per mole. So then our Kb constant for water is 8.314. In retrospect, probably should do this a little lower. So our Kb for water is 8.314 joules per mole Kelvin, times our temperature, our boiling point, times our molar mass, and then divided by our delta H vaporization. And now checking out some unit cancellations here. So we've got this per mole can cancel there. This we're going to need to multiply by 1,000 joules per kilojoule to cancel that and cancel that. And then one of these kelvins will cancel with this. And so what we're going to end up with in the end is a gram per Kelvin mole as our unit. So if we run this through on our calculator, we get 513.06 gram, we're going to get gram Kelvin per mole. So the Kelvin will be on top. Or if we multiply by a kilogram per 1,000 grams, 0.51306 kilogram Kelvin per mole. And now if we return to our temperature change equation, then we have pretty much all the factors you would need for a sugar solution. So our delta TB is going to be, so just rewriting it, I KBB, which is just 1 times 0.51306 kilogram Kelvin per mole times B. Now B is the molality, which is in moles, I guess I'll write it here actually. It's the moles of solute over the mass of solvent. So if we had a sugar solution that was 1 mole per kilogram, So there was 1 mole of sugar per kilogram of water. Then our delta TB would be 0.51306 Kelvin. So our boiling point would be raised by 0.51306 Kelvin. And so to put it more, to hammer it home even more, our final temperature, as it's our delta T, our final temperature minus our initial, which would just be the normal boiling point, would be equal to this 0.513 or 0.51, just to round it to 2 decimal places. And so our boiling point of our sugar solution would then be, so moving this to the other side, would just be 373.66 Kelvin. So now, so a sugar solution that was a mole per kilogram would boil at 373.66 Kelvin. And we can use this same constant for any molality, and so all you need to do is figure out the new molality. Okay, so if we check here, so we've got, here's our boiling point equation. And here's each of the factors. So for sugar, we have I equals 1. So our KB, you can also just look up these values. It's about the same, 0.513, 0.515. And depending on the molality you're given, you would get a different value for your elevation. And of course, depending on the units. So that looks good. Okay. Okay, so identify the effect of increasing acidity on the solubility of the given compounds. So from, just to start off, from Le Chatelier's principle, we're going to expect that increasing acidity is going to increase our solubility. So increasing acidity will increase solubility for basic solutions. And we should be able to verify this anyway. So if we look here, so for zinc sulfide, which has no such line, zinc sulfide, which is going to dissolve into zinc 2 plus S 2 minus. Zinc, so the first 2 columns in the periodic table, right? So zinc 2 plus is one of the alkali earth metals. Both of the first 2 columns form strong bases with OH. The reason why I'm mentioning this is because if we combine this with water, we're going to get zinc hydroxide plus H plus, and so this would be zinc acting as a acid, so accepting OH minus. But that's a strong base, so this does not happen, and it only goes that way. So this reaction doesn't go. S2 minus plus 2 water gives us, maybe I'll actually just leave it like this, 1 water, and make it go to HS minus plus OH minus. In this case, we actually have a weak base. So this guy's a weak base, meaning that this is also a weak acid. And so this reaction should go. And so we would have a weakly basic solution. And so in this case, if we add H3O plus ions, then they will combine with our OH minus to give us water, eating up our OH minus and shifting the solution more to this side, which will in the end shift more to this side because we're eating up our S2 minus. And so then this will increase the solubility. So we'll get increased solubility here with increased acidity. Okay, and again, just to tie back, we get increased solubility with increased acidity for a solution that's weakly basic, because this is a basic salt. Okay, so then if we go on to the next one, so MgCO3. So this is going to dissolve into Mg2 plus CO3 2 minus. Again, this is an alkali earth metal, so that's going to form a strong base and with water. So if we combine this with 2 waters, we would get MgOH2 plus 2H plus, but that's a strong base, meaning it doesn't go back and forth, it just goes one direction. And since that one direction is back, that means we aren't going anywhere near that. So that it's going to just stay in solution like this. While CO3 2 minus, if we combine it with water, we will get HCO3 minus plus OH minus. This is a weak base. And so this will go. So we're going to get a basic solution, and so we're going to get increased solubility with increased acidity. Okay, so we're going to get for a basic salt, increasing the acidity will increase the solubility. Barium hydroxide. Well, barium hydroxide is a base, so we're going to get barium 2 plus 2 OH minus, and in this case we've already got our OH minus. We don't even need to consider whether it will prepare OH minus, so we're just straight up going to get H3O plus OH minus going to H2O, which is going to eat up our OH minus and increase our solubility. So this is basic, so increased solubility for increased acidity. Okay, and then Ca3 PO4 2. So this is going to dissolve into 3 calcium 2 plus 2 PO4 3 minus. Yep. Again, we have a alkali earth metal, so the reaction with water as we could guess, is not going to go. Right, so this here is a strong base, which means this doesn't go, and it just goes backwards. So we only have our reactants, whereas PO4, 3 minus, combines with water to give us HPO4, 2 minus, plus OH minus. Excuse me, which is a weak acid. And so we're going to get OH minus in solution, so this is a basic salt. And so increasing acidity will lead to increased solubility. Okay, so at this point, it's appearing like increasing acidity just always increases solubility. Now for the next one, this is going to dissolve into nickel 2 plus 2 Br minus. So in this case, we have nickel 2 plus, and so again, alkali earth metal. So NiOH2, but this is a strong base. Meaning it only goes that way. So we get nothing happening there. And then if we combine Br minus with water, then we get HBr plus OH minus. And in this case, this is a strong acid, meaning it doesn't go that way. And so everything just stays in solution here. And so this is actually a neutral solution, as we have, as both species are either the conjugate acid or conjugate base of a strong base or a strong acid. And so because it's a neutral solution, or a neutral salt, increasing acidity will have no effect on solubility. And we can verify this because further anyway by saying that H3O, if we add H3O plus to say Br minus, then again we would want to form HBr plus H2O, but as that's a strong acid, it's not going to go. So H2O plus, adding H2O plus to the solution just had nothing to react to it. So increasing the acidity will do nothing to the solubility. And so for then for copper iodide, we have a similar kind of thing here, right? So copper 2 plus I minus. Copper 2 plus is again an alkali earth, or no, it's not, sorry. Copper 2 plus, neither with nickel 2 plus, sorry. Both of these are D block metals. So copper 2 plus, but it should still form a strong base, or at most an acidic solution. Yeah, okay, so then 2 H plus, so this guy is a strong base. Which means that doesn't go. And then I minus plus H2O. And not copper 2 plus, which means this would be just copper plus, and it's actually just a single OH, and I don't need these 2s. Sorry about that. So again, H2O with I minus. It's going to give us HI plus OH minus. That's a strong acid though. So it's not going to go both ways. It's just going to go backwards. And so this is a neutral salt, which means that increasing our acidity will have no effect on solubility. Okay, so basically, if we look, our first 4, increasing our acidity would increase our solubility, but for the latter 2, increasing our acidity should have no effect. Okay, so they mentioned that Le Chatelier's principle states that pH should affect, but they don't say what effect. So if it's a basic solution, it will increase, whereas neutral or acidic, it shouldn't have an effect, or it should have a negative effect for acidity. Okay, so for the first one, increased solubility for increased acidity looks good. Increased solubility for increased acidity for the second one. Same for the third. Same for the fourth. But then for the fourth or fifth, they still said increased, which is incorrect. So for these 2 species, adding H plus will do nothing because we don't want to form HBr and we don't want to form HI. Or those 2 species will actually just go backwards into solution. So 1 to 4 are increased solubility. 6 are no effect. Strong acids. So I'm going to say it's incorrect. Okay. So this one's a quick one. So what is the conjugate base of the ammonium ion? So if we look at our acid reaction for H4 plus, so we react with water and do an H transfer. Oops. Went the wrong direction there. Plus H3O plus. And I'm just going to shift this down. Okay, so then these 2 here are conjugate pairs, and these 2 here are conjugate pairs. And so NH4 plus NH3 are acid-base pairs, and H3O plus H2O are acid-base pairs. Okay, so on the left-hand side, NH4 plus acts as the acid, and on the right-hand side, H3O plus acts as the acid. And then the role of base swaps on left and right as well. So we say that ammonia, or NH3, is the conjugate base of NH4 plus. And you can see that we just remove H plus from the acid to get our conjugate base. working through the solution. So an acid is any species capable of donating a proton, and a base is one capable of accepting said proton. So if we look at the reaction, we can see that ammonia NH3 is our conjugate base. So that looks good. Okay. So what values are allowed for the MS quantum number? So this will be good to just summarize some things. So the typical quantum numbers we're going to see in first year or high school are N, which is our principal quantum number, L, which is our orbital momentum, quantum number, ML, which is our magnetic, and MS, which is our similarly, it's our magnetic electron spin. Quantum number. And so very similarly to these two, where ML can equal minus L plus 1 up to L, MS equals minus S plus 1 up to S, where S is our spin momentum quantum number. But the nice thing about electrons is that our S is always a half, whereas in an atom, L can take on any values from 0 up to n minus 1. But for an electron, S is always a half. And what that means then is that MS is always minus a half or plus a half. So MS is the spin quantum number. It specifies the orientation of the spin axis. And we can just have the two directions, minus a half or plus a half. So that looks good. Okay. All right, so what mass of silver chloride can be prepared by the reaction of 100 mils of 0.2 molar silver nitrate with calcium 100 mils of 0.15 molar calcium chloride. And actually for this purpose, or for these purposes, I'm just going to put a 1 unidirectional arrow, that way it makes it easy on us. And so this is going to be calcium nitrate, which is going to be 2 of those. So just to balance this, so we're going to need 2 of those, which means we're going to need 2 of those, which means we're going to need 2 of those. And just so that things aren't too squished. And then that looks balanced to me, so that looks good. And so just writing out our volumes or our givens, so 100.0 mils, 0.20 molar, 100.0 mils, 0.15 molar. And so our moles of silver nitrate is just 0.20 moles per liter times our volume, which is 100.0 mils. So this needs to be in liters, so 1 liter per 1,000 mils. And so then our mils will cancel and our liters will cancel, and we get an answer in moles, which is just 0.020 moles. And now if we check our moles of calcium chloride, it's 0.15 moles per liter times 100.0 mils times 1 liter per 1,000 mils, which is just 0.015 moles. Okay, so there's our moles of our species that are present in our solution. Now, if we check our equation, we need 2 moles of AgNO3 per 1 mole of calcium chloride. Or to put it more into the terms of our question, 0.020 moles of silver nitrate will react with 0.010 moles of calcium chloride. Okay, so now we've identified that we have an excess, right? So we're only going to be able to react with 0.010. And so that means that we're going to have 0.005 moles of calcium chloride excess. All right. So that's okay. So the first thing it asks us anyway is what mass of silver chloride we're preparing. And so if we look at our equation again, we have 2 moles of AgNO3 giving us 2 moles of AgCl. Right? So for every 2 moles of AgNO3, we get 2 moles of silver chloride. Right, so then 0.020 moles of silver nitrate will give us 0.020 moles of silver chloride. Right, although it's a 2 to 2, it essentially is a 1-to-1 ratio, and so after reacting 0.020 moles of silver nitrate, we're going to end up with 0.020 moles of silver chloride. So to get the mass of silver chloride, we're going to need our molar mass, which is just the molar mass for silver plus the molar mass for chlorine, which is 107.87 grams per mole plus 35.45, which comes out to be 143.32 grams per mole. And so then our mass of silver chloride is the molar mass multiplied by the amount of moles, which is our 143.32 times 0.020 moles. So our moles cancel, giving us a value in grams, which comes out to be 2.866 grams, or rounding to 2 significant digits, 2.9 grams. And now the other question it asks is the concentrations of each ion remaining in solution after precipitation is complete. So here, we have initially to consider that we have our silver nitrate. Actually, I guess we might as well just go by our posted products. So our products are calcium nitrate, so we need to consider that, and and then the excess calcium chloride. So we know we have excess 0.0 what did I say? 0.005 moles of calcium chloride from excess, and also from looking at our equation, for every 2 moles of silver nitrate we form a mole of calcium nitrate. So 2 moles of silver nitrate forms 1 mole of calcium nitrate. And so put another way, 0.020 moles of our silver nitrate will form 0.010 moles of our calcium nitrate. All of these will dissolve in solution, so writing them like this is actually kind of pointless. So calcium nitrate is going to dissolve into calcium 2 plus 2 NO3 minus. And so looking at this solution, this equation here, so if we have 0.010 moles of this species, then we're going to get 0.010 moles of calcium 2 plus and 0.020 moles of NO3 minus, because we get double. Okay. And then looking at our calcium chloride, which is going to dissolve into calcium 2 plus 2 Cl minus. We already know we have 0.005 moles excess, so we're going to get 0.005 moles of calcium 2 plus and 0.010 moles of chlorine. Okay, so then the ions we have in solution then are calcium 2 plus, which the amount of moles from summing these two values is 0.015. Our nitrate is 0.020, and our chlorine is 0.010. Now to get our concentration, we need our volume. We poured in 200 ml solutions, so our volume is 200 mils. And so then our concentration of calcium 2 plus is our moles over our volume. And now molar is typically in liters, so we're going to want to multiply 1,000 mils per liter, canceling the mils, and giving us 0. Why didn't I write this down? Oh, right, 200 mils, sorry. 0.075 mils, 0.075 molar. Okay, and then our concentration of NO3 minus is 0.020 moles over 200 mils times our 1,000 mils per liter, which comes out to be 0.1 molar. And our concentration of chlorine which is the same, or calculated in the same way, I should say. Canceling units everywhere. 0.050 molar. Okay, and so there's our concentration of all our ions left in the solution. Okay, so looking at the solution here, so we identify the number of moles, identify our limiting reagent, and then find the mass of silver chloride by identifying the number of moles and finding the molar mass. So it comes out to be 2.86 grams. So it's about what I got. And then rounded to 2 segs would be 2.9, but that's okay. And then the concentration of our remaining ions, so 0.075 molar, 0.05 molar, and 0.1 molar. So that looks good. So those all look good to me. All right. Okay, so for each molecule, what is the polarity of the bonds and the overall polarity of the molecule? So we can't see all the molecules there, but I'll go through them. But I'll draw them as I go through them. So, so our first one is CH2Cl2. So if we draw this guy, so it's going to be a tetrahedral shape where I'm using the wedges to show it's coming out of the board and the hash to show that it's going into the board. I guess I should use a slightly more appropriate convention than I've been in the past and draw my dipoles from negative to positive. So here we would have a dipole. Here we would have a dipole. Although you will get a minor dipole from carbon-hydrogen bonds, it's definitely not going to be as high as for carbon-chlorine, which means that, and because this is a bench shape, so if I kind of tilt this like this, then our hydrogens would actually be more like that, and these are now coming out of the board because I've rotated the molecule. So if we look now, we can see that we're going to get a net dipole in that direction, basically. And so CH2Cl2 is polar with the net dipole basically into the page as I've drawn it in this image, but a little bit up, so similar to water, basically, where these hydrogen atoms are basically where the lone pair would be. Okay, so for HCN, again, our hydrogen-carbon bond is going to be a minor contributor, but the nitrogen-carbon bond is going to be polar, meaning our net dipole, and in fact this would be a minor one that way, our net dipole is going to be along the nitrogen-carbon bond, but to the left. And then for our Third molecule is H2O2, which is kind of a funny shaped molecule because it does this, where the wedge is coming out of the page and the hash is going into the page. Or if we tilt it 90 degrees so that we're looking at the oxygen end on, then we would have something that looks pretty much like water. The only difference is that this hydrogen is actually displaced into the background, but also similar to water, we've got two dipoles, and so then the net dipole is actually going to be pretty much straight down, which cuts the molecule in half. Okay. Okay, so for a bond to be polar, the difference in electronegativity, so this is, I guess, more of a numeric definition. So CH bond is technically nonpolar, as I said, or as I basically indicated by having these smaller arrows, whereas a CCl bond is definitely polar. So for our first molecule, we get two large dipoles for carbon chlorine, and then we're going to get a net dipole because of a lack of cancellation. In HCN, we again have no dipole with the hydrogen, but a dipole between the carbon and nitrogen, giving us a polar bond. And then in H2O2, because of this tilt, we're going to get dipoles in the OH direction, and it's going to be a polar molecule. So that looks good. All right. How do you solve for Ka when you have the molarity of the acid and the pH? Okay. So if we consider kind of our general acid equation, we have this, where if we put things into the definitions that we have in the question, and we form our little ice table, then our initial concentration of HA, I'm just going to call our concentration of HA, and we have 0 of these two. Our change is going to be minus X, and our equilibrium value is then our concentration of HA minus X, X, and X. And so our Ka can always be found by X times X over our concentration of HA minus X. But now if we look, that's our concentration of H3O plus at equilibrium. And our pH is the negative logarithm of our H3O plus concentration, which is just our X value. So it's the negative logarithm of our X value, which means that our X value is related to our pH as 10 to the minus our pH. Now putting this into our Ka, we can say that our Ka is 10 to the minus pH times 10 to the minus pH over our concentration of HA minus 10 to the minus pH. Or, just for the sake of rearrangement, minus 10 to the minus pH over 1 minus our concentration of HA over 10 to the minus pH. So then our Ka, so that this equation has our Ka in terms of purely just pH and our acid molarity. All right, so writing out the Ka from our acid equation, we can use an ice table to put these values in. Yeah, so basically they've explained that we can just use this to find our X and then plug it into our Ka expression. And we don't really need an equation, but this looks good. Here's I have an expression here that we can just plug in the values for. But that's fine. What is the hybridization of NH3? So hybridization is just a SP designation in this case, which essentially describes the orbitals which have been hybridized together to give us our bonding orbitals. Just rewriting NH3 over and over again. So for NH3, we have N and our hydrogens, and we can link these all up, which gives us our molecular structure, which I'm going to use hashes for into the board and wedges for out. And so counting the lone pair, we have 4 bonding partners, and so we would need this to be an sp3 hybridization. Right, so 1 plus 3 equals 4, so there's 4, again including the lone pairs, 4 partners, so we need 4 total, which means it must be sp3 hybridized. So that's kind of the easiest way to pick out what the hybridization is. Yeah. Also, it's with the lone pair, it has a tetrahedral geometry, which is always our sp3 hybridization. Okay. The hybridization can be identified using the steric number. The steric number is the sum of the bonding electrons and the number of lone pairs. So as I said, just sum it up. And so we must have sp3. So that's good. Okay. All right. Write the electron configurations for magnesium and argon using both SPDF and orbital box diagrams. Okay, actually I wanted to have this here. Okay. Just so that we can find things. So for magnesium, he's sitting here, and actually I probably shouldn't be continuing to use this periodic table because I forgot my argon is, so there's magnesium, and argon's here. My argon is not H, it's argon. Okay, so to get our electron configuration, we can stick helium over here, as this is our S block, our P block, our D block, our F block, and the F block inserts in here. And so to get our electron configuration, we just run across. So for magnesium, it'll be 1s2, 2s2, 2p6, 3s2. And so there's using SPDF notation, and then and I might as well do argon while I'm at it. So argon is going to be similar to magnesium, so 1s2, 2s2, 2p6, 3s2, and then we need to add in this 3p6. Okay, and then using orbital box diagrams. So for magnesium, we're just going to draw boxes for 1s, 2s, 2p, and there's 3 orbitals for 2p, and then a symbol for 3s, and each one gets 2 electrons, which are paired. And so that would be the orbital box diagram for magnesium. And for argon, 1s, 2s, 2p, 3s, and 3p. 2p, 3s, 3p, and again each one is paired. So there's our orbital box diagram for argon. And the relationship of an electron's configuration to its position. As we can see by looking down the table, right? So in the second column of the table, we have very similar configurations where all we're really increasing is our principal quantum number. But in each case, as we run down the alkali earths, we're just going to have our relevant S shell filled. And then for the case of argon, we're in the noble gases, which will change with the principal quantum number. But the P shell will always be filled. And in fact, for the noble gases, we will have our complete subshell filled. 2 electrons in its third shell. So basically the configurations will be very similar as we go down the table. So I'd say that looks good. Solution is correct. That looks good. Okay. So here's our next one. So in nitro chloride, there is no oxygen-oxygen bond. Write a Lewis structure for the molecule and write any resonance structure. So there's no oxygen-oxygen bond, which basically tells us that nitrogen, so just counting up valence, but nitrogen's likely the center. So we've got 5 valence here. We've got, for oxygen, we've got 6 times 2, which equals 12. So 2 for the 2 oxygen molecules, and chlorine will have 7. So summing these up, we get 24 valence. Okay, so then trying to do this in kind of an easy way first by using the normal valence. And oxygen and then chlorine. Okay, so we can connect this, we can connect this, we can connect this. And if we look, we've got a full octet here, and we've got a full octet here. But then these guys here are not full and not full. So the easiest thing to do would be then to move an electron over here and use this guy and this guy to form a bond. As that way we'll keep our octets, but then we'll see what comes of that. So if we redraw that, we've got this with a double bond to oxygen and chlorine. And now if we count up so now we see that everyone has a full octet. If we count up our electrons around each of the species, we have 1, 2, 3, 4, 5, 6, 7. So we only take half of so there's 2 electrons on a bond, but we only take half of that for how many is actually around it. So there's 7 electrons here, which means this guy has a 1 minus charge because there's 1 extra. And here we have 4 electrons, so we have a 1 plus charge because there's 1 too little. Here we have 6 electrons, so that's neutral. And here we have 7 electrons, so that's also neutral. So we've got a structure here where there's only 3 bonding partners, so it'll be a trigonoplanar molecule. So drawing it now with a bit more structure. And so now we have full octet everywhere, but our charges are separated. So we've got a plus charge on the nitrogen, a minus charge on the oxygen. But also we have some resonance possibility because this could happen to give us a very similar structure. Where now the negative charge is over here, the positive charge is still on the nitrogen. And now, so the negative charge is actually shared among the oxygens, which helps to stabilize the structure. Okay. And so I'd say that's the final structure for our nitrile chloride. So we counted up 24 valence electrons. I didn't ever check it, but I'm pretty sure all 24 are there. And how did we get, I guess I wouldn't say we would be able to get that resonance structure, but that one's a bit far-fetched on the left, because now nitrogen has 5 bonds, which is a bit out of this world for nitrogen. For the species beyond nitrogen, it's fine, but I would say nitrogen wouldn't be too happy with it. So I think I'm happy with the 2 that I've drawn, but I guess technically that one is a resonance structure, but I would go with the 2 I've drawn. So that's it, the solution is correct. 5 bonds to Ed is a little far-fetched. Okay, so which of the following combinations of N and L represent real orbitals and which are impossible? So just to refresh here, when we name orbitals, say 2s, that means that N equals 2 and L equals 0. So N can be 1 up to infinity. L can take on values from 0 up to N minus 1. And so that's our real restriction here, is that L can't be greater than n minus 1. And that's kind of what we're going to be looking for. And then just to link this back to our SPDF notation, L equals 0 is S, 1 is P, 2 is D, 3 is F, and from there it just goes alphabetical. Okay, so now back to the question. So for a 2s orbital, we have n equals 2, L equals 0. So that looks good because L is less than n minus 1, or less than or equal to n minus 1. So 5D, n equals 5, L equals 2. So that looks good. L is less than or equal to n minus 1. For 3F, n equals 3, L equals SPDF3. So then in this case, this is not good because L is not less than or equal to n minus 1. Right, so this one is impossible. And then for 3s, n equals 3, L equals 0, so that's good. L is less than or equal to n minus 1. Okay. So checking the solution here. So just going through that, and then so the first two are real, the third one's impossible, and the fourth one's real. So that all looks good. Okay. Now consider the following compounds. And so with these 12 compounds, we get different structures. Draw the Lewis structures for each and predict the molecular structure. And predict the bond angles and polarity. Okay, so for CO2, so we get 4 from carbon. So counting out valence, 6 times 2 equals 12 from oxygen. So 16 valence electrons. So this guy is going to be our typical oxygen with a double bond to carbon and each of the oxygens. So we get our full octet. If we count, we have 2, 4, 6, 8, 10, 12, 14, 16 valence electrons. So that looks good. So then this is our molecular structure, which is linear. And although there are dipoles from oxygen to carbon, they will cancel, and so it's non-polar. And our bond angle is 180 degrees. So for our next one, SO2, so now we have 5 valence, and 6 times 2 for oxygen, which is 12, so 17. Now if we try to draw similarly, so we're going to get a double bond to sulfur, but then we're actually only going to be able to form a single bond to the oxygen and then hold a lone pair on the sulfur. And actually sulfur has 6 valence electrons, sorry, so there should be 18. I got carried away a bit there. And so now everything is a full octet, but we have a -1 charge on the oxygen and a +1 charge on the sulfur. But we also have resonance structures And then due to the lone pair here, we're actually going to get a trigonal planar electron geometry. So writing this as a molecular geometry. It would be more like this, so a bent shape. We definitely have a dipole along this direction, but of course, because of the resonance structures, this charge is actually being shared. Giving us a dipole along both bonds, and that's too many electrons. And if you recall, a resonance structure doesn't mean that it bounces back and forth between the two, but it's actually a superposition or an average of the two structures, meaning that the real structure is something more like this. With partial negative charges on these two and a definite positive charge on the sulfur, meaning we have dipoles in these directions and so a net dipole in this direction. And because of the lone pair, this bond angle will be less than 120 degrees. The molecular structure is bent and it will be polar. Okay. KrF2. So krypton is a noble gas. So we'll have 8 valence here. These are both halogens, so 7 times 2 equals 14. For krypton to form any bonds at all, we're going to have to move its some of its electrons, but we can do that. So krypton will at least have to do it this way. So split a pair of electrons, which we can do as we move into the D block. And so that'll give us our bond there, with 3 lone pairs on krypton. And so then if we draw our molecular structure, so there would be a lone pair here, a lone pair here, a lone pair here, and then fluorine, and fluorine. And so this is actually a linear molecule. Our bond angle is 180 degrees. And although there would be dipoles, they will cancel, so it's non-polar. Okay. Sorry. SO3. So we have 6 valence from our sulfur, and 6 times 3 equals 18 from our oxygens, so 24 total. We're going to need to have 3 bonding partners here. So our sulfur is going to need to have 3 electrons available. So we're fairly certain that to get an octet, we're going to have to do something like this. So I'm drawing 2 little electrons there now. I'm going to go ahead and pop that on this oxygen here, just kind of as a shortcut. But then we're still going to have trouble getting our octet. So that guy would have a -1 charge, which means the only way that we're going to be able to make this happy then is for this to actually form a double bond here and here with these guys. Okay, so then we're going to actually have something more like this. Where that's negatively charged, that's positively charged, and these two are neutral. But that looks pretty good, and it's going to be a trigonal planar structure because it's only bound to 3 species. And so then we're going to have something like this. Okay, with a negative charge here and a positive here. But of course we have resonance structures. And so in reality, the charge is shared around the ring. And the real structure is going to be something in between. Similar to this, where we now have a positive charge definitely on the sulfur, and the negative charges are shared around. So what that means is that we've got a perfect 120 degrees in here, and the dipoles will all directly cancel, meaning this guy will be non-polar. And it'll be a trigonal planar structure. Okay. I might have to pick this up later. Okay, let's see what I can do here. NF3. So for NF3, we've got 5 valence here. 7 times 3 equals 21. So 26 total. So our nitrogen typically has 5. Our fluorines like this. And so this is actually a nice normal structure, or one that we're used to. Drawing this as a molecular structure. With wedges to show it's coming out of the page, and dashes for into the page. So we've got a trigonal pyramidal structure. And then these angles are less than 109.5 degrees because the lone pair has kind of squished them down. There will be dipole moments between each of these, and they won't cancel, so there will be a net dipole upward, and so this guy will be polar. Alright, IF3. So IF3, we've got 7 here, 7 times 3 equals 21, so 28 total. Our iodine, just to skip some steps here, is going to need to have 3 available for bonding, which means its other 4 electrons are going to be in lone pairs. So it must have split one of the lone pairs for bonding. Okay. And so then if we draw our molecular structure here, then we're going to have iodine. Our lone pairs are going to be at the side. And like this. Now these are, because of the lone pairs, are going to be less than 90 degrees, as it's going to squeeze it down. And this bond angle is going to be less than 180. There will be a net dipole towards the fluorines. These two will cancel, but there will be a net dipole that won't cancel here. So this will be polar. And the molecular structure is T-shaped. Okay, CF4. So for carbon, we have 4 valence. Each of the fluorines has 7, which is 28 total from the fluorines. So the total is 32. And here again, we have something more akin to what we're used to. Where these guys should all bond together. And so this is going to give us our tetrahedral CF4 solution, or tetrahedral CF4 structure. Okay, so these are all 109.5 degrees, tetrahedral. And although there are bond dipoles along each of these, because of the symmetry, they will cancel. So this guy is non-polar. Okay, SF4. So here we have 6, and 7 times 4 is 28 for a total of 34. Our sulfur is going to need to form 4 bonding partners. It normally has 6, so it's going to just keep a lone pair. Okay. So we have, so this guy is going to be something like this. Where that's going into the page, and I have this lone pair coming out of the page. And so this is a seesaw structure. It will be polar due to non-cancellation of our dipoles. And these angles, because of the lone pair here, will be less than 90 in here. So everything will be squished together a little bit. And yeah. Okay. And then xenon F4. So we've got 8 valence there. 7 times 4 equals 28. So for a total of 36. Our xenon is going to need to have 4 bonding partners. but it has an extra couple electrons, so I'll just plunk them there. And like this, so we got our bonds. And so then our molecular structure is, so I'm going to put the lone pairs below and above, and I'm going to draw these coming out of the page, going into the page, coming out of the page, and going into the page. And then each of these angles in here is going to be our 90 degrees. This is a square planar structure. And although we have dipoles in here because of the symmetry, this guy is going to be nonpolar. Okay, now PF5. So phosphorus has 5 valence electrons. Each of these contributes 7 for 35 and a total of 40. So for PF5 to have 5 bonding partners, all 5 of its valence electrons must be split. Okay. And here we go. And so then we would have a structure like this, where those are out of the page. Okay. And so then although there's dipoles in here, they would all cancel. And so this guy's nonpolar. That's a 90-degree angle. These are 120-degree angles. The structure is trigonal bipyramidal. Okay, and a couple more. IF5. So here we have 7. Here we have 5 times 7, which is 35, for a total of 42. So iodine needs to have 5 bonding partners, and then it's going to have a lone pair. And just sprinkling these around. So these are all going to bond nicely. And so we've got iodine with, draw this, okay. A lone pair up above, fluorine coming down, and then these are coming out of the page, going into the page, coming out of the page, going into the page. And so these angles here are going to be less than 90 because the lone pair is going to squish them, and these here are also going to be less than 90. There will be a dipole towards the iodine, which, because of the deviation from a symmetric structure, is going to lead to a net dipole. So this will be polar. And then for our last molecule here, SCl6. So sulfur has 6 valence. Each of these contributes 7 times 6, which is 42. So then in total it's 48 electrons. Each of sulfur's 6 electrons must be available for bonding to bond to 6 partners. Okay. And so it must be something like this, which if we draw it would be each of these going this way, coming out of the page, going into the page, coming out of the page, going into the page. And so this is an octahedral structure. Each of these angles is 90 degrees. And although each of these bonds would be polar, there's perfect cancellation, so this will be non-polar. Okay. So that's all of them. So going, I lost it. Okay, going back to the top here, we have CO2, which is linear, bond angle of 180, and it'll be non-polar. SO2, which is bent or V-shaped, and it will be polar. And the angle will be less than 120. KRF2 is linear with a bond angle of 180, and it will be non-polar. SO3 will be a trigonoplanar structure, which is non-polar because of the cancellation, and a bond angle of 120. NF3 is going to be pyramidal or trigonal pyramidal, bond angle of less than 110, so about 107, and it will be polar. IF3 is a T-shaped molecule with 90 degrees in here and 180 degrees from the fluorines, and it's polar because of its lack of symmetry. CF4 will be tetrahedral with angles of 109.5, and it's non-polar because of symmetry. SF4 will be a seesaw shape, and it will be polar, and the angles will deviate from ideal conditions due to the lone pair. XEF4 is square planar. All the angles are 90 degrees, and it will be non-polar because of the symmetry. PF5 will be trigonal bipyramidal with angles of 90 degrees here and 120 degrees on the equatorial, and it will be non-polar. IF5 is square pyramidal, and it will be polar, and bond angles will be less than 90. And SF6 is all the angles will be 90. It's an octahedral structure, and it will be non-polar. So that looks good. All right, and I'm actually going to stop this here and say thank you all for watching. I hope you enjoyed this. If you did, please subscribe to OneClass. If you want to leave questions, please follow the links below the video. My name is Jeff Krause, and I hope to